I'm not. Hey, Christian. Hi, Christian.
Okay, all right. Let's. My goodness. We're recording now. My goodness.
Hello, YouTube.
Sorry, Christian, I won't say hey anymore.
We have fun in class, don't we?
I do, yeah.
Okay, good. All right, is this going to show up? There we go. TV's on. Let's get started. Okay. So I have two topics for today. One of them is going to be one that I don't really make you do. It's going to be one I just show you, which is how to construct the influence line for trusses. In other words, the internal force inside members. There's not a lot of mystery to it, though. There's really, you're just going to sort of do it in a brute force type fashion. And you'll see what I mean when I show you how to construct an influence line for truss members. My real thing, though, today that I want to deal with is fixed supports. Because we've been drawing influence lines for internal shears and moments, we've been drawing them for reactions, but we've been looking at simple supports or like pin roller type boundary conditions, and we haven't looked at a fixed support. And fixed supports are surprisingly easy, but sometimes I've noticed students make them out to be more complicated than they are, so I'm going to try some like artwork here on the board to maybe clarify what's going on here. But we're going to do a cantilevered beam today to try and illustrate, okay? Let me take my keyboard off here, and let's see, did everybody get the code? Everybody get the code? All right. Okay, so let's go through and discuss fixed supports. All right. Okay. Okay, so the idea still remains that we are moving a load across the structure, recording a response at a point of interest. But we are also still using the Mueller-Breslov principle to actually construct the influence lines. I would argue that probably today, more than Monday and Wednesday, that base definition of an influence line where we're moving the load across the structure is probably going to be more important from a gut check perspective to make sure that you understand what we're doing and why we're doing it. We are still removing from the structure the ability to resist that response, and we are moving that structure through a unit deformation. Okay? Now, here's the thing. Let's talk about fixed supports. Okay? None of the rules that we've talked about so far are inapplicable to fixed supports. I mean, they still work. Okay? But how they work and how you properly apply the rules for fixed supports is something that requires some attention. Okay, so let's take a look at something. Here's a fixed support. Okay, now let's consider the influence line for the vertical reaction. Okay, so I'm drawing an influence line. Okay, so what do? I remove from the structure the ability to resist this vertical reaction. And I move this structure through a unit displacement. Here's the thing. I take the support and I move it through a unit displacement, but I don't remove the rotational restraint. Okay? So look right here. This is wrong. Okay? This is wrong. Okay? If you take your support and move it through a unit displacement and start constructing your influence line like this, that's wrong. Okay? Let's see how my art works. Okay? So I want to keep in mind when we remove from the structure the ability to resist a reaction, we're only talking about that reaction. Okay? So this might be sort of an elaborate image, I'll say, but let's assume that we've got this fixed support, okay? And what I want to do is remove from the structure the ability to resist this vertical reaction, but only the vertical reaction, okay? So let's imagine, how would we craft a support condition that removes the ability to withstand vertical reactions, but can still resist bending, okay? And so I came up with this the other day. I think this is probably like the easiest way to do it. So, excuse me. So imagine you had a beam, and on the end of the beam, you had this plate, something like this. Okay, and so the beam goes out like this, okay? And let's say this beam is affixed to a wall, okay? So here's the wall in the background, or some column. Here's the column, okay? And let's assume that it is affixed with slotted holes, okay? So I've got this hole going through the plate that looks like this. Let's put two of them on there. Okay, and let's say that I've got bolts like this. Going like that. And let's say that's my support condition. I know it's a little bit of an odd support condition, but let's just say that that is my new support condition. Does this connection for this beam, so we're talking about this beam right here, does this connection resist loads left to right? Like, can I yank it this way, and will this support condition resist those loads? I would say yes, right? Like, if I take it and I pull it, the bolts are going to keep it there, okay? Now, on the flip side, what if I take this and I lift it up and down, okay? If I lift it up and down, will it resist up and down motion? No, it'll freely go up and down, at least as long as there's travel here, okay? Will it prevent rotation? Like, is it going to be easy to take this and turn it? No, right? Like, I can't take this and sort of turn it like that, because I'd have to turn like the whole plate, and these bolts are going to prevent that from happening. Does that make sense? Okay, so here's what I'm getting at. You have a fixed support, okay? If you say, okay, Dr. Mike wants me to draw an influence line for the reaction in A, so I'm going to take point A, I'm going to lift it up, and I'm going to draw my influence line like this, like I've been doing all the other influence lines. That is wrong, because what we're doing is we're removing the vertical support reaction, but not the moment reaction. So how do you translate it? You translate it like this, okay? All you're doing is lifting the entire segment up, okay? It's all going up, and it's going up flat, okay? Does that make sense? Okay. Likewise, okay, let's think about, so this would be a vertical reaction release. So what would a moment reaction release look like? Well, that was pretty easy. So if we had a fixed supported beam, really all we're talking about is just changing it into a pin or a hinge, right? Because now we can very easily take that element and rotate it. Put a little pin right there, okay? It's going to resist translation this way. It's going to resist translation this way, but it's going to be very easy to rotate, okay? Does that make sense? All right? So this is what would happen if we were a moment reaction. So a moment reaction is basically taking this and turning it to that. That's basically what we're doing for a moment reaction release. But for a vertical reaction release, we're essentially resisting moments, resisting horizontal reactions, but not vertical ones. Does that make sense? Here's my point. Let's just do a problem, okay? I want to draw several influence lines for this. Here, I don't know why I accidentally created a page there. I want to draw several influence lines for this problem. Okay, so let's get set up. Come on. Okay. All right. Let's draw some influence lines. What influence lines do I want to draw? Well, let's start off with our reactions. Let's draw an influence line for AY and an influence line for MA. Okay. Let's assume that you don't like this. Let's assume that this is like you're having a hard time wrapping your head around these images that I drew here on the board. And you're like, what is this gobbledygook here? That's fine. Okay? Let's not use this. Let's ignore Mueller-Breslau. Well, what is the fundamental standard definition of an influence line? We move a load across the structure and we record the response at the point of interest, right? Okay. So let's do this. All right. Let's consider the following. All right. Let's say we have our fixed support. Here's our beam. It's 20 foot long. All right, let me move this down. All right. And I'm going to place a load right here. I was very scientific about where I placed that load along the span, wasn't I? I just put it somewhere. Let me ask you a question. What is the vertical reaction right here? What is AY? What is it?
1.
1. But does it matter where I put it? All right, let's investigate what Mr. Cartwright's saying, okay? Let me move this up a little bit. Okay, so Mr. Cartwright is saying this right here is 1.0. Let me ask you a question. Does it matter if I put the load here? Does it matter if I put the load here? So what you're saying, Mr. Cartwright, is I can put that load anywhere across the span and AY equals 1. That no matter where the load is, the vertical reaction equals 1. Is that what you're saying? Yes. That's 100% correct. Okay? So much so that I propose that the influence line for the vertical reaction at A is a horizontal line. So what I've done is I'm giving you two different explanations, okay? There's this explanation here on the board, which is the Mueller-Breslau explanation, which is I move the support through a unit displacement. So what would the beam look like? Like imagine this was the beam, and I pick the beam, and I move this up one. I'm picking the entire beam up, and it's just whoop, shifting up like that, okay? That's the Mueller-Breslau explanation. If you don't like that explanation, what about just the basic definition, okay? Take this load, move it across the structure, what's the reaction? Wherever you place the load, the reaction is 1. So there's your influence line for the vertical reaction at A. Does that make sense? Okay. What about MA? Let's try this. Okay. Let's throw a little bit of algebra into the mix. Let's take this load and let's place it there. Where is there? Some distance x from the support. And let's say that my moment reaction faces like that. Okay. So how do I solve? Let's ignore all this Mueller-Breslau, hinge, gobbledygook. Tell me, how do I solve for the moment reaction today? Tell me what to do. Some moments a day. So let's sum moments a day. Okay. So what do we got? So we've got, we're summing moments a day. Do we have to consider AY? No. Nope. What about MA? Do we have to consider that? Yep. And so put MA over here. And what goes on the other side? 1 times X. Okay. So would MA equal positive X? Or maybe a better way of stating it, X going like that, because it's a positive answer and we assumed that. So maybe what I'll do, just to enhance some clarity in my influence line, is I'll say that counterclockwise rotations are positive. So if that's the case, what would my influence line look like? Let's be clear, this is a coordinate system, right? This is my y-axis. This is my x-axis, so this is x equals 0, x equals 10, x equals 20, right? Along this x-axis. So what does it look like?
A linear line.
What's that?
A linear line.
Okay, so tell me what it is here.
0.
What is it here?
20.
20. So, this, exactly right. So this that's the influence line for the moment reaction today. I mean, bless you. Does that comport with the Mueller-Breslau reaction? Here's my cantilevered beam. Take this fixed support, turn it into a hinge, take that, move it through a unit rotation, right? So what essentially I'm doing is I'm turning it into that, right? I'm picking it up like that, right? Okay, now in order to do that, the slope of this line needs to be 1. What is the slope of that line? A rise of 20, a run of 20. See it? So what I'm saying is these cantilever beams are not hard, they're easy. That's my point, they're really easy, okay? And by the way, this works even if the problem is a little strange. All right, let me give you a strange one. Let's give you an odd one. All right, bear with me. You'll see what I'm doing. Let's get silly. All right, so let's assume that I've got a really out there structure. Okay? Now, we're going to make this determinate, by the way. So I'm going to put like a roller here, a roller here. I'm going to put a roller here. And then, wait, hold on. That's not what I want to do. How do I want to do this? Let's do a roller here. A roller here. That's what I want to do. And a roller here. And then in between, so we've got a fixed ended beam, 3 rollers. So I'm going to put 3 hinges in there. I'm going to put a hinge here, hinge here, hinge here. Like this is a really odd one. Okay? And let's draw the influence line for this vertical reaction. So what does the influence line look like? Okay? So what do we know? Let's go back to our basic definitions. Okay. All right. We know that the influence line is going to equal 1 right here, right? It's going to equal 0, 0, and 0. Is that a fair statement? So what would the influence line for that vertical reaction look like? Okay, I've got to pick this point up, so I'm picking this up. This is flat. Flat. And then seesaws the rest of the span. So, whoop, whoop, whoop. Like my sound effects? That would be your influence line. Really, really odd shape, but I mean, is it really all that complicated? 0, 0, 0 at the supports. We pick this up, straight line segments across the board. Does that make sense? Told you there was a plan there. Okay. All right, before we move on, is everybody okay with this? Does this make sense? Okay. Okay. I'm lazy, so I get to do that. So I just copied and pasted it over again. All right. So now I want to do 2 more influence lines. I want to do an influence line for the shear at B and an influence line for the moment at B. Okay. Anybody here do any like swimming or diving or anything like that? You do. Okay. I'm going to call on you then. Okay. All right. So let's assume, for the sake of discussion, that this cantilever beam is a diving board. Okay? What happens if here's the diving board? Let's make it a really long diving board. Let's draw 2 mirror images of them, just so that I don't have to keep drawing this twice. Okay. Now let's say here's me in my hyper-technical schematic, and I'm standing at the edge of the diving board. The diving board is going to bend down. Is everybody in agreement with that? Would you say that the entire length of the diving board, from end to end, is being bent. Like the whole thing's, it's like a bowstring, like the whole thing is being stretched. Everybody okay with that? Now, let's take this scenario and let's say that I'm standing right here. I haven't yet got to the end to make my jump. Okay, so what's happening to the diving board? Does the diving board flex down? Well, yeah, it does bend down a little bit. I'm not saying it doesn't. But what happens out here? The diving board's just sort of going along for the ride. It's not flexing it. The flexing happens from here to here, right? That's where the diving board is seeing stresses and strains. Out here, the diving board is just sort of going along for the ride. Like if here's the diving board, and I'm stepping like right here, and the diving board keeps going on out, it's just there. It's not seeing any force. I'm not saying it doesn't deform any, because this is, but it's just sort of going out in space. Does that make sense? Does that make sense? Okay. All right. So let's take a look at the influence line for the shear at B. So what do? I put a shear release in. Okay? I used some terminology yesterday that I told you I was going to clear up. I said that we say this goes down, this goes up. But I didn't say that. What I said was the left side tends downward. The right side tends upward. Right? You know what I said? So I guess what I'm asking is, I'm going to draw an influence line. Is that right? Drawing the influence line like that, is that correct?
Probably not.
It's not. Okay. Why is it not? Okay, well, there's a couple reasons why it's not. First off, what's happening here? This point is rotating, right? But I installed a shear release. I didn't change anything here. This point cannot translate or rotate. It's got to stay flat. If it doesn't stay flat, it's bending. What did I tell you? Influence lines are lines. They're straight. There is no curved segment in a determinate influence line. So this can't deform. It's got to be straight. But let's also just think about this, okay? I am drawing the influence line for the shear right there. What is the shear right here when the load is here? What is the shear in the diving board when the load is present right there? Zero. I propose that the influence line needs to be 0 throughout this entire region. Would it be fair to say that this point on the diving board is not going to experience any stress, any strain, until I get over here? Would that be a fair statement? So I propose that the influence line for shear at B looks like that. And when we do a shear influence line, what is the total amount of jump? 1. Does this comport with the rules that we said that a shear influence line has to follow? The total jump has to be 1. Didn't we say the total jump has to be 1? And what else did we say about this line and this line? Their slopes have to be the same. What is the slope of this line and this line?
1, 0.
0. But they're the same. They're the same. Does that make sense? Everybody okay with that? I propose that the influence line for the shear at B looks like this. Similarly, the influence line for the moment at B is going to be 0 and 0. And what do we do when we install a a moment, or what do we do when we're drawing a moment influence line? We put a hinge at the point of interest, right? And when we do a hinge, we're trying to rotate this side some. We're trying to rotate this side some. They tend to rotate that way so that we have a total slope of 1. But I propose this side has to stay flat because this is a fixed support. It also comports with this reason here. So, what does our influence line for moment at B look like? It looks like that. Why am I drawing it downward as opposed to upward? Because the diving board makes frowny face. Okay? It's a negative bending moment diagram. If I were to plot the bending moment diagram for the load over there, the moment diagram will be negative across the board. Okay? And if the slope of this line is 1, that makes this minus 10. That, ladies and gentlemen, is the influence line for the moment at B. Does that make sense? Anybody have any questions on that? Did I get my diving board analogies correct? Okay, thank you. All right, any questions on this? Everybody good? All right. Let's look at trusses. Okay. So the one thing we haven't discussed is the influence line for a truss. And when I say influence line for trusses, what I'm talking about is the influence line for the axial force in a given truss member. Okay? I want to be clear that the Mueller-Breslau principle does work theoretically, but it doesn't work practically. And by practically, I mean what you would have to do is imagine you have a big truss, remove one of the members from the truss, and then take that member and make it a unit longer or a unit shorter. And then what does the truss look like when you do that? I don't know about you, but I can't see that in my head. If you could see that in your head, great, but I can't do that. So I think that the only practical way of constructing an influence line for a truss is just brute force. And what do I mean by brute force? Move the load across the structure and analyze the truss at every placement. I know it's a pain, but there's really no other way around it. Okay? Fortunately, software like MathPan and whatnot can make that a little bit easier for you. So the only thing that I think is worth mentioning in a way that will remove one bit of ambiguity is where do you put the load? In other words, do you move the load across the bottom joints, or do you move the load across the top joints? Because it will change your answer. Okay, that's crystal clear. And the answer that I would give you is move the load across the structure wherever the road is. Okay, so for example, if I was looking at this truss over here on the left, I would take the load and move it across these bottom joints. So I would put a unit load here and analyze the truss. Put a load here and analyze the truss. Put a load here, here, etc. Why am I putting them on the bottom joints? Because that's where the cars are. Okay. Whereas for this truss, I would put the load on the top. Okay. Does that make sense? Like, it's not like with beams that this wasn't like a question. Just put the load there and move it. But with trusses, you do have to like make that decision, and that's my answer, is just put it wherever the road is. Okay? So just to show you how this works, and you all aren't going to have to do this, by the way. This is all movie time. You can just watch. All right? I want to construct the influence line for the following truss. Okay? So I want to and when I say the influence line, I'm picking a few members. Okay? So I'm picking members AB, CD, FG, CF, BF. Okay? All right. So what we're going to have to do in order to construct these influence lines is bless you. We're going to have to move the load across the structure. So essentially, we're going to have to put the load at A, load at B, load at C, load at D, and load at E. Okay? Now, does somebody see how at least two of these analyses are a waste of time? Which two are a waste of time? A and E. Because if I put the load at A or I put the load at E, what is the internal response inside the truss? 0. So that's done. The rest, though, we got to kind of deal with it. But do we have to do 3 structural analyses? I mean, what is the difference between placing the load at B and placing the load at D? What's it going to do to our results? It's going to do that to them, right? Because this truss is symmetric. So I really only have to analyze the truss twice. I have to put the load at C, and I have to put the load at B. And whatever I get the answer for the analysis for the load at B, just invert my answers, and that's going to be the load at D. It's a bit repetitive. It's not hard. It's just repetitive. So the first thing to keep in mind is that you can still use the Mueller-Breslau principle for the reaction influence lines. So the vertical reaction in A, 1 3/4, a half, 1/4, 0, and then for B, 0, a quarter, half, 3/4, and 1. We can do that, okay? But past that, it is just kind of brute force, okay? So here's what I have here on the next slide. So what I've done is I've analyzed the truss with the load at B, and here's the answer. And I've analyzed the truss for the load at C. Here's the answer, okay? Does that make sense? Now, at least for this bottom one thing we can do is recognize this is a totally symmetric structure. So all I have to do is analyze from here over and then flip my answers. And then again, for B, all I have to do is take this truss, flip it, there it is for D. So let's see if we can come up with some influence lines. So let's look at member AB, okay? So member AB, if I place the load at member AB, okay, at joint B, I'm getting 1 in tension. So I'll say this is +1. I'll say tension's positive, +1. Okay? What about the load at C? If I put the load at C, I'm getting this as 2/3. So this is +2/3. Now what about the load at D? How would I get the answer for the load if the load's here? How would I get that answer? I would flip. So what member am I looking at?
B.
Say again? Somebody said it. What did they say?
B.
No, well, hold on. Okay. Okay, so let's make sure I'm clear. I want the force in this member when the load is at joint D. How do I use this information to get that? I'm going to take all these answers and flip them. So what's the answer?
1, -1. Wait.
Does everybody see what I'm talking about? All right, hold on. Eyes up here. Let's focus. Okay. Does everybody agree that this is the complete result of the truss analysis when the load is at B? Okay, everybody agree with that? Now, this is what I'm proposing. I'm imagining printing this out on a sheet of paper and then taking the sheet of paper and flipping it over. What number am I going to see right here?
Oh, 1/3.
There we go, 1/3. There we go. I'm going to see +1/3. Does everybody else see that? Does everybody else see that? Everybody good? Okay. All right. So that's member AB. Let's try member CD. So member CD, what goes here?
1/3.
1/3. What goes here?
2/3.
Okay. What goes here?
1.
What?
1/3.
All right. Hold on. All right. No, hold on.
Does that really help?
Okay, hold on. Let's do it really big. You ready?
Oh, 1/3.
All right.
Why is that so hard?
Okay, all right. Now let's do member FG, okay? So what goes here?
2/3.
Not quite.
Negative.
There we go.
1/3, 15 fractions.
There we go, negative 2/3. Okay, so here it's,
Negative 4/3.
there we go. And what goes here?
Negative 2/3.
Negative 2/3. Does everybody kind of see the pattern? Everybody kind of sees the pattern. Okay, so at this point, would you agree if I just showed you this? See? So you see what we're doing here? Like what I have here on the board is literally what I have here on the slide. So I'm basically saying the load at A, the load at B, the load at C, load at D, load at E, and I'm just recording those responses. Okay? So what do I have here is these responses, but I also kind of like to look at this. Okay, member AB and member CD are on the bottom of the truss. Okay? Member FG is on the top. The diagonal is CF. BF is a vertical member. The reason I'm showing you that is there's very specific shapes of the influence lines dependent upon the type of member that you're looking at. So let's look at those. Member AB and member CF. So look, let's take a look at member AB. This is just 0, 1, 2/3, 1/3, 0. 0, 1, 2/3, 1/3, 0. That's just me plotting that. The whole thing's positive, right? It's all positive. Why is it all positive? Because it's a member on the bottom of the truss. When you move a load across the structure, the truss, let's assume it's a beam. Like a truss is just a beam with really big holes in it, right? So imagine a truss goes like that, the bottom's in tension, right? So as the load moves across the structure, there's no way this member isn't in tension, right? Same thing with member CD. It's in tension too. But why is member FG, why is it negative? Because it's on the top of the truss, and the top is experiencing compression, right? So what's going on with the diagonals? The diagonals, those are the members that are in the middle of the truss, and they're kind of like the ones that are resisting, like if we thought of a truss like a beam, the diagonals are kind of like resisting shear. So what happens is they kind of reverse from compression to tension depending upon where the load is, right? Now, what is this gobbledygook with BF? That's my word for today, is gobbledygook. Why is member BF like this and it's like 0 everywhere? Because, like, take a look at this right here and this right here. When the load is over here, take a look at this joint. That's a 0 force member. That's a 0 force member. A while back we talked about 0 force members, and y'all asked me what is the point of a member in a truss that isn't carrying any load? And my answer to that is that's if the load is there, but what if the load moves? If the load is there, that member's seeing load. And with bridges, loads move, right? So there is one load position where the loads may be 0, but there is another load position where they're not, right? Does that make sense? So what I'm saying is, like, this is, like, first off, I do want you to recognize the pattern. I will also be candid about something. There is a practice problem. Like, I had a problem when I took the FE exam, and I was given a truss problem, a truss influence line, and it was, here's the truss, what does the influence line for member CF look like? And I looked at it and I said, C, move on. Because it was an inner diagonal member, and I knew that internal diagonals flipped. If it was a bottom chord member, I knew it would be negative across the board. If it was a top chord member, if it was a bottom chord member, I knew it would be positive. If it was a top chord member, I knew it would be negative, right? I was able to look at the truss, look at the configuration of the truss, look what member it was looking at, and just, boom, that's the answer. And I didn't even need to do any, like, calculations or math. I just looked at it, moved on. That was a fast question on the FE. There's a reason for all this, I promise. So. Any questions? I am giving you 4 minutes of your life back, ladies and gentlemen. You have a wonderful, wonderful weekend. Next week, we're going to start using these influence lines for structural analysis directly.